So for today, we are going to discuss on the buckling of columns. So probably the Euler buckling formula and its applicability for to engineering related problems. So we know that if we recall our fundamentals, let's say you have an element. So we apply uniaxial loading. Let's say we apply tension. So what can happen to this? So if we draw the stress strain curve, so we call this the engineering idealization. Otherwise, the actual one would be something like this and it like this. So let's say, so the probable failure mode to fail this by tension is by yielding, right? So the stress, let's say this is P. So if the cross-sectional area is A, P over A is your stress. So when your stress exceeds the yield stress, so we call this the material has yielded, right? So in the similar manner, you can go for compression members as well, but in the compression, apart from the yielding, you have another one called buckling, right? So what is actually buckling? It's a state that the member tends to lose the stability, right? Loss of stability, and this is governed by several factors, but I would say like this. So still the Euler formula is pretty much widely used for buckling, so which can be written as this Euler formula. So he showed that the critical buckling load can be written as phi squared EI over L squared. So which governs, so this is pin ended, both pin ended. Okay, so and E is the Young's modulus, I is the second moment of inertia, phi is 3.14, L is the effective length. I'll call you what is effective length actually, LE. Okay, so this really does depend on the end conditions as well. So that this is for a pin condition. In general terms, this can be written as PCR critical as phi squared EI over K times LE squared. So in that case, we don't need actually LE, K times L squared. So this K times L is the effective length, right? So this LE can be written as K times L. How it's possible? So depending on the end condition, so this L effective means, I don't think, probably you have heard this. So the L effective means the distance between zero moments. That's it, right? For a pin end case, right? So you know at the pin ends moment is zero, right? So you know the total length would be the L effective. So that it is equal to total L. So that means K is 1, right? K should be 1 in that case. For a fixed one, right? Let's say for a fixed case, you know, so if you apply some loading, so the distance between zero moment is this length, right? It would look like this, right? So that's some factors. So I don't really remember that factor. I think it's 0.7. No, you have to check that. So this has been provided in the appendix, any of the appendix actually. So depending on the end conditions, this is changing. Actually, the K factor will give you, right? If it is fixed, for instance, let's say K is 0.7. So then you have to K times L, right? L is the total length, right? So this is the general equation. And this is written then in general form. This is still applicable in engineering applications. But there are, so you can, one good observation is that when this term is getting maximum, right, this will be maximum. So that for the same material, right, for the same length, you can see that, so K maximum is uh, K maximum is 1, right? Sorry, not 1. So it can be 2 as well. So when the K is increased, let's say for a free end case, so we know the buckling shape would look like this. So we have to complete that part, and that would give you twice the L, right? 2 times L. So don't worry on these factors will be given to you. If it is fixed, the factor K factor is given. If it is fixed pin, K factor is given, even in the design codes as well. Let's say you are designing a concrete building. So in the design guidelines, when the columns are checked, they ask you what is the K value, right? So that depends on the end conditions and whether it is pinned or fixed, right? So depending on that, we idealize the K value and calculate design for buckling, right? So for now, keep this in mind, right? For a pin condition, this K is 1, right? So you can see when the K is increased, right, beyond 1, so this would, so the total term would decrease, right? So when the K is lowest, buckling force will be higher, right? So the force required to buckle the column will be higher, right? When the K is low. So this particular Euler formula has some assumptions. I would say it is not the perfect, but still it's hold some considerable values, right? So Euler formula assumes that load is exactly applied at the centroid, right? Without any eccentricity, right? Without any eccentricity. But in the real life, you don't have such direct loading applications. You have some eccentricities, right? So when you have eccentricities, right? Let's say your column is this, so your load is applied this. So this is your column. So when the load is applied, as soon as the load is applied, due to this eccentric moment, so PE, let's say, so the moment is applied now, so your column will start to deform. But when it's applied at exactly along the centroid, so it will not deform until it reaches the buckling load, right? So if for this case E is 0, right? For this case E is non-zero. So for 0 case, if you check the loading versus deformation curve, right? So you will have something like deformation. So let's say this is the deformation, this is the loading. So for E equals 0 case, I will draw it in purple color. So since your load is acting along the centroid, right? No deformation is observed, no deformation is observed. Suddenly, when it reaches the critical buckling load, a sudden deformation will occur. So this is the case where you have for this, right? But for the with eccentricity, so as soon as the load applied, you will have an eccentricity, right? And this governs you another thing, that this moment, due to this moment, your critical buckling load calculated in these steps will be further reduced, right? So in the actual conditions, right? Actually, we have some eccentricities, right? Anywhere else, right? So this is for non-zero case, right? So this is for E equals 0. It's a pre-critical, right? So let's check some of the videos. So you can see that this is pin and this is pin end. So if you calculate the critical buckling load, so K is 1, right? K is 1 and phi is 3.14. These material things are given so that you can calculate the critical buckling load as this. And this will depend on, so that means when it is increased up to 100,000, when it is, so this is the Euler assumption. Load is at the acting along the centroid. When it is increased up to the up to 1,000, suddenly it will buckle, right? Until that no deformation is observed, right? So another thing, so if you have a section like this, so this is a section, so you can see along x axis, right? So you can calculate some I value, and along y axis you can calculate some second moment of inertia value. So you can see that Ixx is lower than Iyy. how could I say that? So I is, as you remember, BD squared over 12, right? If you haven't seen that, please check on my videos on moment properties of plane areas. That explains you everything. So this is going to be, so I in that video I told you if it is Ixx, so the third power, the cube will always set to the length which is cut by the axis, right? Which is cut by the axis. So axis is xx cut by this length, right? Is crossed, right? So that will be bh cube over 2l. If you check along y axis, that will be hb cube over 2l. So b is considerably larger than h. So that iy, that means hb cube over 2l is larger than bh cube, which is ixx, right? So that from this equation, you can see when the I value is low, critical buckling value will also be low. So that you need to consider the axis with lower inertia value, right? So in this case, Ixx is critical. That will give you the lowest buckling load. Let's say that Ix with Ixs you calculate 1000. With Iyy you will calculate some, let's assume that will be 4000. So the buckling loads are given. So the critical buckling is the lowest one. When it is 1000, it buckles about x-axis, right? So it will never reach 4000. Why? It has already buckled, right? So you can go ahead and you can see it depends on the fixed and pin condition, fixed free conditions, so that you can uh, calculate different k values, right? So these k values will give you, so the inflection point. So as I told you, so the effective length means distance between zero bending moments, right? So you can see, you can set this into imaginary length until the inflection point is obtained, right? So at the free end, you know zero moment. So you take the mirror image. So the your effective length will be 2L. And likewise, you can calculate the effective length, right? So fixed, it's, I think it's, yeah, it's 0.5, not 0.7. So fixed pin, it's 0.7. So this is nothing but the uh, uh, distance between zero moment inflection points. So for pin, this is LE is L. So that K is 1. For this case, K is 0.5. For this case, K is 0.7. For this case, K is 2, right? So that K tells you what is the factor, right? Here you can see. So you have to substitute L effective for this one, right? So what K value which should be applied, as we have to based on our assumptions when you especially design a building, right? Even in trusses, right? You have compression members, so that you should ensure that it will not fail by buckling, right? That's another criteria that you have to. So you can see that when the length is low, your critical buckling value will increase. That means when the length is very small, it will reach to infinite, right? So that we can write something like this, actually. So your buckling load y squared EI over LE squared, right? So you can check the buckling stress critical. So you have to divide it by the area. So you know, I divided by A. What's that? The radius of gyration, right? Okay. So this can be written as I over A means R squared, right? So you can write this final equation as this pi squared E LE divided by so this is critical buckling stress, right? So keep this in remember, right? So we can see that. So we call this term the slenderness ratio, right? Effective slenderness ratio, LE upon R, right? So if we draw a curve, sigma by LE, right? It would look like this. It would look like this, right? At when the LE upon R is very low, so you will have infinite buckling load, right? That's the buckling stress. That's this curve tells you. But can you have infinite buckling? No. There's another criteria which fails the which governs the failure there. What's that? Yielding, right? So the material crushes. Material have some compressive strength, right? Compression, yielding, right? So it will fail by compression. So this is then the curve, right? So that there will be a critical value, right? So this is the critical slenderness ratio, right? Where your buckling stress and the critical yielding stress is equal, right? At that stage. And for that, for low in this region, your buckling load, that buckling stress is higher than the compressive stress. So that means failure is by crushing, right? So think about very small column. So it will never buckle, right? So something like a concrete cube. Have you seen when the concrete cube is compressed? It is not buckling, right? It fails by pure compression, right? Because the effective length is low, such that it will have infinite buckling load according to this mathematical formulation. But when the length is increased, so your buckling will be lower than the compression yielding, right? So that it will fail by buckling in this region, right? But the experimental curves will not exactly fits into this. It will look like this, right? Experimental observations, right? So at higher slenderness ratios, so the experimental observations are in accordance with the Euler formula, But in this region, you don't have such agreement, right? So in compression, we need to check two things. Your Euler formula is valid when the sigma critical buckling, I would say this is buckling, right? That should be lower than your yielding by compression. Otherwise, it will fail by compression, right? Under this assumption only, you can use the Euler formula, right? So we'll do an example. So I'll show you how some video on how that buckling experiments can be performed. So I hope you can see this video, nice video. So you can see this is, so under this assumption only you can use the buckling formula, right? So sigma gamma means sigma yielding, right? So let's say for fixed conditions. So please check this, how this failure is occurred, right? So the length is 10 meters, so it is loaded. So it is fixed and fixed. So suddenly, can you see? This is buckling, right? The material, can you see? The material did not fail in compression. It lost it it lost its instability, right? So that's how it failed, right? So we'll do an example. So this is our first example. So that tells you the A36 steel bar has a square cross section and it is pin connected at ends. Determine the maximum allowable heat that can be applied to the frame. It's a factor of safety of 2, right? So by looking at this, you can see that this will have a tension, this will have a compression. How did I say that? This is a vertical force acting downwards. At this joint, this is perpendicular. So this will have no connection with this load, right? This perpendicular force cannot stop this P. So that means only this force can stop this P, right? Can equilibrium, bring this P into equilibrium. So that means if it's in the vertical downward direction, the force which required is should be upward direction, so that you can have the component of this force in this direction. That's how this become a tension, and you can calculate that. Let's say this is P1. So P1 sine 30 is equal to P, right? P1 sine 30 is P. So sine 30 is half. P1 is 2P, right? So let's say this is P2. Okay. So now again, so you should consider the horizontal equilibrium at this joint, right? If this force is in this way, so the component of horizontal component will be in this way, right? It will be in this way. So that means the member force of AB should be in the other direction to balance that. So P2 should be equal to P1 cos 30. So you can write 2P into cos 30. So that brings you 1.73 times P. Right. Okay. So they need a safety factor of 2 times, right? So that means if this is your buckling load, right? So let's think our force in the member is F dash. So if your critical buckling load divided by uh, critical so that they ask at least, so if your critical buckling stress, buckling load, right, and your working condition, the working load, the ratio between these two is the factor of safety, right? So let's say if your critical buckling load is 100, right? So that means our working load can reach maximum of 50, right? If it is larger than 50, let's say 60, the factor of safety will reduce 1 point something, right? So we need factor of safety of 1 2, right? So this this can be lower than 50. Let's say if it is 25, so you have factor of safety of 4, right? So that means your working load can only reach 50, right? In this case. So that's how we incorporate the factor of safety. And this is 2. This is your load. So this is your critical buckling load. So this is phi squared EI over LE squared, right? So you can isolate F term so that phi squared EI squared. So for A36, right? So you can determine the buckling load, right? So you know the E values, right? So the section is given so that you can calculate I value. So E value is known from the tables, and then so it's I value, and then you know this is a truss, right? So you know the connections are pin, right? So pin. So it doesn't matter. This is a tension member. So this is the compression member we need. This is what we need, right? So P2, right? This is P2, and yes, then pin conditions. So it's 10 feet, and you can calculate. So 10 feet means that is 120 inches, right? So okay, so one one foot means 12 inches, so that 12 into 10 is 120 inches, right? So and then it's 1, k is 1, this is L, right? So k times L give you the L effective, right? So from this you can calculate. So this would be the peak critical value, right? So the buckling load. But still, so this critical value is equal to, so if you apply a P load here, so the load on this is 1.7 times 73 times P. You are not applying a compression direct load to this member, but you apply a vertical load such that this member will compress. If you apply P here, the load on this member is 1.7 times 73 times P, right? So that means if the load in this member is 1.73 P, so you have, it is for a P load at here, right? So this, so if you, so you consider the buckling load of this, right? Okay, so let's say this is buckling load is P, okay. So earlier we saw if P is applied here, the force in this member, compression member, is 1.73 times P, right? Similarly, if the force in this member is P, you need to divide it by 1.73 to obtain the loading hung at P, right? So if P is applied, 1.73 times P is here, right? So that's the compression, the working load, right? So your P critical over, you remember this one, P, this is the P critical, right? F critical or P, whatever, right? So let's say P dash is the working load, right? So P dash multiplied by 2, right? So P dash is actually 1.73 times P into 2, right? So these two are equal, both P critical, so that you can calculate the P value, right? You can calculate the P value, right? So P value would be 2.42, right? From that, you can take into this equation and calculate P critical value. 1.73 times P times 2. So that will give you something around that will give you a value around 1.73 times 2.42 times 2, 8.37. So that's the critical buckling load, right? Right. So we have calculated the buckling value to ensure with ensuring that, so this is the P value that can be hung at that point, right? P is this much. If you apply this much, right, there will be a factor of safety of 2. If you increase it, right, if you increase it, factor of safety will not be there, right? At some point it will reach. So if you apply P, let's say it's like this, so this is 2.4 times 8, so That means this is 1.73 times 2.42, right? So, and the buckling load is exactly now twice of this, right? When you increase this, right? When you increase this will not fail, right? This will not fail, this will increase, but factor of safety will not be there, right? Factor of safety now is 2, and it will come from 2 to I will draw it in this way, so that you will understand it clearly. Let's say this is 1 kilonewton. This is let's assume the force is 2 kilonewton. Okay. Buckling load is, let's say, 8 kilonewton, right? Let's say the crushing value, the pure compression value is fairly larger, right? So we have to consider, I'll talk that later. So the factor of safety is 8 upon 2 is 4, right? So when you increase it, let's say you increase the force here, let's say let's say the ratio between these is 1/2. If this is 1.5, this will be 3 kilonewton, right? So that your factor of safety is reduced, right? It's 2 point something, right? Likewise, you can increase this until it reaches 8, right? If it reaches 8, factor of safety is 1, right? Exactly 1. So if it is less than 1, it will fail, right? So factor of safety 1 means it's verge of failure, right? In the verge of failure, it's about to fail. So to be it's 8, you have to apply 4 kilonewton, because we assume that the ratio is 1/2, right? Ratio is 1/2. That's why this is the example, and the same thing has been done here as well, right? So one more thing, now for this you have to divide this by this big the critical value divided by the area, right? And take the sigma critical value, and you have to make sure that it is less than the yielding value. Otherwise, you can't use the Euler formula, because you are working in this section, right? Where the failure is by buckling. If you move to this position, failure will be by pure compression. So we will make sure that the stress is less than the compressive stress, right? So that it will fail by buckling first, right? It's like this. Let's say the column is this. Let's say for buckling, you need 50 kilonewton. For compression, you need 100 kilonewtons. So this will fail by buckling, because the force, when you increase the force from 0, it will reach 50 first, so that it will buckle and fail. Let's say your buckling force is 200, and this remains as 100. Now you are in this region, right? Now you are in this region where your compressive strength of the material is less than the stress that can be withstood when the buckling occurs, right? So it will fail by, because the lower value is now this, right? It will fail by crushing, right? Before reaching buckling, right? You have to understand which comes first. Under this phenomena only, you will work out on buckling, where it is less than the yielding, that means the compressive strength of the material, right? Compressive stress, right? So if it is not exactly along the middle, we have a secant formula, right? As I explained here, the same thing, right? So when the loading is just applied, it will have a deformation, unlike the Euler assumption, right? So this will be the actual scenario, right? In that case, you can calculate the maximum deflection using this equation, right? So you need to work out these problems to understand this, right? So we did one example, right? So if it is not, if your sigma y value is given, so that means the yielding value is given, that means you need to check both yielding and buckling, which comes first, right? And your Euler formula can be used if and only if your buckling stress should be less than the sigma y value, right? Okay. Thank you.